Okay, so yeah, so I'm glad to come today and show some of the most recent research work we have done. Actually, I'm a Berkeley graduate, so some of the funders and then early developers of Spark were my former professors or were my colleagues. So to me, it's just a great opportunity for me to come to the Spark Summit that came out of a Berkeley project and say what research today can do to revolutionize data analytics. Okay, so with that, let me start. So we all know that a key feature of Spark is unified data analytics. So today I want to talk about a unified data analytics optimizer. We'll automate all the optimization tasks or that can be done like a SQL optimizer. So scalable data analytics systems have gained widespread adoption, but our work is motivated by fundamental limitation of scalable data analytics systems. So let me just describe, how analytics users, how a user has to experience today. So let's assume, we have a click stream, and we have one user, Bob, who wants to run a SQL analytics on this stream. So the SQL query looks somewhat complex. So basically it says, I want to join clicks with pages based on the URL, and then I want to group the join results by the user ID. And then within each group for a specific user, I want to compute average page rank. If the average page rank is greater than 0.5, I want to output this user with this average page rank. So basically, this query computes users with good taste. If he tends to visit pages with a good page rank, he belongs to the answer set. Okay, so that is the common task we're going to do on Clickstream. But let's assume there's a different user, Alice. She wants to run, machine learning jobs on the same stream. For example, she wants to sessionize the Clickstream, and over the sessions, she wants to train a classifier to predict the user buying intention based on, the clicking behavior of a particular website. Okay, these are very common analytic tasks. So in order to execute these tasks, so cloud computing comes across as a pretty good choice. So let's go to the cloud. But then how do we actually go about it? If you look at Amazon EC2 today, even if we don't consider spot instances, there are about like 30 cloud instances for the user to choose. They differ in the computation power and the memory available. Okay, so kind of the right choice depends on the workloads, the performance needs, and the user budgetary constraints. Today, it's a guess done by the user. And then, if he's lucky, he gets the right instance. If not, he has to repeat this choice process. So even if, this user has settled for a cloud instance, when you actually run a Spark job, there are over 100 parameters for the user to configure. So we call those parameters the job parameters or the job configuration. So what do those parameters cover? They talk about the degree of parallelism, how many parallel tasks I will compute. They talk about the memory allocated to each executor. And if it's a streaming job, it talks about granularity of scheduling, which determines the latency. So there are lots of parameters the user has to worry about. And then again, the right choices, really depends on the user performance goals. For example, latency here determines how much latency this user has to experience once all the relevant data is there, while throughput captures the number of bytes or records we can process per second, right? For critical analytics, these really are objectives of the user, and then they have to, they determine the right configuration of this of those runtime parameters. So today there's no support. It's up to the user to configure these parameters, and it is a trial and error process. You start with the default configuration. If you're not happy with the performance, then you tune it until at some point you find the performance satisfactory, probably by even using a larger cloud instance. So this is a very iterative trial and error type of process. Let's imagine one day Alice finds a bug in her code, and now she needs to rerun the analytics over all the data archived on disk. So while the previous job configuration was tuned for, say, latency, and now she wants to maximize throughput so she can bring the data from disk as fast as possible to catch up on the analytics. So because now the performance goal has changed, she has to redone all the she has redone the tuning process. Okay, so I guess my key point here is, today's analytics service only guarantees availability as LSA, the service level agreement. And then there are too many configuration choices are left to the user. So for example, my colleagues, my former students, they're like chief data scientists of many companies. On a daily basis, they're struggling with those configuration choices in order to save company money while achieving the desired performance goals. So we're presenting a major, providing a vision. So we want to transform the paradigm of analytics in the cloud where the user has to make so many choices to a new paradigm where the user only declares, these are my workloads. Either it's a SQL query or it's kind of a sequence of machine learning steps. And then in addition, I have these performance requirements. I want the latency to be less than 5 seconds. I want the throughput to be greater than 1 million tuples a second, and have my monetary constraint is X dollars per day. That is all the user has to say. And then the rest is done by an optimizer. We call that, it's a unified data analytic optimizer. Technically, it's actually a Dataflow Optimizer. I'll define Dataflow just in a second. So because my background is the databases, so I think, a key point here is, a fundamental task in the design of a SQL database is a query optimizer. Okay, so basically the user only says at a high level, I want to compute as such. The user does not have to worry about how to go about for the most highest efficiency. So we want to bring the same culture, the same kind of strengths beyond SQL queries, but to the broader class of analytical problems called data flow programs. So that's why we call this the extension of the optimization theory from SQL optimizer to a data flow optimizer. And as an initial step towards the vision, today we'll show you how we can actually automatically tune the job parameters given the user high-level, description of his workload and his objectives. So in the future, we'll also extend this to the choice of cloud instances, including spot instances versus dedicated ones. So by doing that, this line of work has the potential to transform how cloud computing is done for future analytics. Okay, so that is our vision, but we're only at the initial stage, so let me tell you what we can do in practice. So now let me precisely define a data flow program. So a data flow program is a programming paradigm where a program is captured as a directed graph of data sets flowing through operators, so there are no side effects. So either the user job is a SQL query or something else, we can compile it into a data flow program. So in the technical world, we'll call this a logical execution plan because it's kind of modeled as a graph of operators with data sets flowing through. And then at this stage, a lot of optimization can be done. I remember in the previous talk, people asked, can you actually, reduce number of shuffles? The answer is yes. There's this logical optimizer that is already in place in Spark and many other systems. By leveraging certain properties, it can decide to change the order of the operators or merge multiple operators into one by removing unnecessary shuffle stages. So, this is well understood in the optimization community. And then similar for machine learning tasks, we can also compile it into data flow program. And there's also a logical plan. But once we got those logical plans, actually, in order to execute, we have to map them into physical plans where we specify how many executors, how many cores, what's the memory allocation per executor, what's the granularity scheduling, what is the shuffling algorithm used, so on and so forth. So there are many, many operators to be determined. So sometimes, you just use a default configuration, but if you really care about performance, really care about dollar amount spent, those parameters need to be carefully tuned. So that is what the optimizer will do for you automatically. Okay? So then what is hard about building this optimizer? So, the first challenge is to build an optimizer that can automatically choose the job parameters based on user objectives. First, we need a cost model for each user objective. And these objectives can be arbitrarily defined. It can be throughput, latency, utilization, I/O speed, any objective the user likes to define and that can be actually measured. So how can we come up with a cost model for every single user objective that he specifies? So I like to explain the challenges by drawing the contrast between a Dataflow Optimizer against a SQL Optimizer. So I guess the first difference is that SQL Optimizer only works for very few operators from relational algebra. We fully understand what those operators do, the semantics, so on and so forth. But the Dataflow Optimizer has to handle arbitrary programs in Python, in Scala, in Java. So there's no semantic description of what those programs do. So it's much harder to do optimization for these arbitrary black box programs. The second difference is that even with 40 years of research, what a SQL Optimizer can predict is only the resource consumption. And it's simply a weighted sum of CPU and I/O counters. Even today, a SQL Optimizer cannot tell you how long a query is going to take to run. If you ask it to predict in seconds, it cannot do. Okay? So the model is very, very simple. While when we do this new type of optimizer, we really want to predict latency, how long it's going to take for the user to see the answer, how many bytes that will flow through the system. So we're actually predicting precise numbers that can be compared to existing observations. So it's a much harder predictive problem. And then the third difference is the SQL Optimizer only cares about CPU and I/O performance, while to model the system behavior in a very complex like Spark environment, we have to worry about CPU, I/O, shuffling, queuing, data skew, straggler, failure, so on and so forth. So there's a much bigger range of tasks we have to handle. And finally, when we go to the cloud, we also have to worry about homogeneous versus heterogeneous hardware. So with this long list of differences, I just want to convince you that it is a major effort to build a cost model for an arbitrary user objective. But deep learning carries its potential. I'll come to that. So the second challenge is that in the multi-objective space, there's not a single optimal solution. So think of in stream processing, you may care about the latency of your answers. You may also care about the throughput, how many bytes the system can process. The two solutions can be both optimal, like 1 million tuples per second with 1 second latency versus 1,000 tuples per second with 0.1 second latency. Okay, so they're both optimal, but there are trade-offs. And then if you look at cost and the latency, it's the same thing. If you care about both objectives, one optimal solution can be 1 second latency at $800 a day. Another optimal solution can be 5 second latency at $300 a day. So the key point is that once the optimization moves to the multi-objective space, the solution is no longer a single point. It's a set. It's a set that can be visualized as a surface, which is called the parental frontier. So the optimization has moved towards computing a single point, which is optimal, versus computing a whole surface that represents trade-offs between different objectives. So again, we can also compute this automatically. So, in this talk, I don't hope to get into too many technical details, but let me at least get a high-level message across. So how do we deal with the first challenge? How do we build the cost model? So that's where, we start to exploit two ideas. The first idea is in situ modeling. So this means we don't expect in priori to build a model that describes what happens in a complex computing environment. We learn that model in situ, in the same computing environment as the job is being executed. So this way, even if the system behaviors vary from one environment to another, hardware varies from one to another, we're learning a model for that specific environment for its own behavior. That's why it has a chance to adapt. Okay? So the second idea is that, we think deep learning carries its potential because deep learning has two key benefits. The first one is representation learning. That means, even given arbitrary programs, if we have their observation of runtime performance or runtime behavior, we can go through representation learning to learn something that characterizes its fundamental behavior. So this property allows us to use deep learning to address the first challenge that, we're dealing with arbitrary programs. There's no semantic description of what it does. The second benefit of deep learning is actually we can learn an arbitrary complex function, which is nonlinear. So this allows us to learn for arbitrary user objective, with complex system behavior and even over different type of hardware. Okay, so let me just explain at a high level how things work. So as you can see, the optimizer only takes two things from the user. One is the user program, the Dataflow program. The other one is a set of objectives. You can define your objectives, and you can even label, hey, the first objective, priority high, the second objective, priority low. Or you can give some weight, saying the first objective 0.7, the second objective 0.3. So all of these are possible for you to specify your preferences. And then what we do is we start with a default configuration. We run it. In this case, we run Spark streaming. And then we collect runtime traces through Spark listeners and OS monitors. So in the end, at runtime, we observe the actual user objectives, the measurements for those, and then the Spark level traces and OS level traces. So we only collect traces, we feed to the optimizer, and then optimizer will develop some good understanding of what this program does, and it will automatically recommend a new configuration based on the user objectives. Okay? So that is what optimizer does. And then if one day, as I said, the user switches from the online mode to the replay mode, the user wants the system to maximize throughput, it just needs to change its objectives. For example, now the throughput gets a higher weight and the latency gets a lower weight. At this moment, optimizer already has a pretty good understanding of the program, so it can automatically output a new objective, a new configuration. And then, this is done automatically, either when the job executes next time, or through Spark streaming, we just wait for the next mini batch when we get a chance to change its configuration. So I guess I will skip some of the details, but I'll give you a sense what happens inside the optimizer. So this is a diagram inside optimizer. As you can see, again, the Dataflow program user objectives come in, and at the runtime, the trace collector returns observations. We actually, in order to build models, we have two paths. One path we have to go through training, so that's a longer path. We send up observations to database, we go through the training phase in order to build models. There's a faster path where we don't go through training. We can directly build a set of models with one model for each user objective. So basically, this module returns a set of functions with one function per user objective. It will be used as a predictive model as parameters are tuned. And then that optimizer takes all these, these functions, and then it runs its internal optimization to take into account user preferences, and then to return, either the frontier, the parental frontier for the user to see and then to make a choice, or it can automatically decide based on its own algorithms, what would be a better configuration. So this is how the optimizer operates. And as I showed in the previous example, once the user objectives or their weights changes, the optimizer will automatically use what it has already stored or computed and then decide on the next configuration. Okay? So the key point is that the user gives very minimal input, only his programs, his preferences, everything else is done automatically. All right, so I guess in the interest of time, I will skip a lot of the technical details, the math. And then, so basically, to build those models, there are two types of approaches. The first type of neural network build is called the embedding approach, where it has one single architecture. You can see that the blue box is the embedding of each workload, and then the yellow box is actually the current job configuration. When we combine them, we can predict the output metric, and then when we actually have the real observation, we take the difference, we do back propagation, so we learn both the neural network, the weights, and then the embedding. So that is one approach. So there's a different approach called Autoencoder Approach, where we break neural network into two architectures, where the first, is simply to learn the encoding of each job. And then there's a second neural network architecture. It takes the encoding, it takes the job configuration, it does the prediction. So there are a lot of technical details. I don't expect to get into the details, but just to give you a sense, the neural network has to do two things. One is to extract encoding from arbitrary program, and the second thing is actually to have this predictive model. So let me show you what we can achieve. So we run a benchmark with about 56 SQL-like jobs, and then 12 machine learning jobs. They're actually trained together. So there are two types of metrics. The first type of metric is we have seen this job before, like 4 or 5 times. And now we change the configuration, how accurate we can predict the performance for objective. For example, latency in this diagram. And then the second actually metric is different. It says this is the first time we see a job. We never saw that before. First time we see a job. We want to predict its performance when we change the configuration, how accurate we can be. Okay, so that is a harder metric. So I just want to show you that this is kind of a state of art as of 2015 using static models. As you can see, this is the error rate, so the lower the better. So you can see the static models will have pretty high error rates. And then embedding approach works in some cases, but for the unseen jobs, the error rate can be pretty high. So the autoencoder approach with necessary optimization managed to cut down the error rate to within 10%, even if this is a job we see the first time. Okay, so it really shows that the neural networks have the potential to learn an accurate model in that right environment. So in the interest of time, I probably will not show you how the multi-objective optimization works. There's quite a bit of math and algorithm design. But let me show you the end result you see. So this is our integration test. So we run Spark streaming, and we have this range of about 50, 60 test jobs. So we take actually maybe 70% for training and 30% for testing. So in the end, we have this 15 jobs for testing. And then we started with a default configuration chosen by experienced Spark user, and then the performance in the latency throughput diagram is a blue dot. Okay, it tells you right now, using this configuration, you'll get this much latency and then that much throughput. And then when automatically we optimize, the performance goes to the orange dot. Okay, so if the point it goes to, or this line goes to the upper left, that means we're reducing latency at the same time we're gaining throughput. Okay, so we're winning both objectives. But if the line goes, to the upper right, that means we're losing a bit on latency, but we're gaining on throughput. So this is a trade-off between two solutions. So out of this 15 test jobs, for 10, we're winning in both objectives, and for 5, we're exploring trade-offs. And back to my replay example, if one day the user wants to replay, by bringing data from disk, you can see the optimizer can automatically jump from that blue dot to the red dot. So because here, we totally sacrifice latency, but we want to maximize throughput. So this is done automatically with actually no time delay because optimizer has already computed enough to make that recommendation. So the key message I want to deliver here is that as an initial step towards the vision of a unified data analytics optimizer, in situ modeling based on deep learning has the potential to model any user objective in a given computing environment. And then multi-objective optimization indeed has the potential to explore the trade-offs and move in the direction of better performance automatically on behalf of the user. Okay, so with that, I just want to thank our funding agencies. So the EU has invested heavily on this project, as well as the US funding agencies. So with that, I'll take questions. Thank you.
Hi, thanks for the interesting presentation. So if I got it correct, you train cost models using deep learning, then you use these cost models to, in an optimization routine, to find a solution on the perioptimal surface. So I wonder, how did you represent the constraints, global constraints, like budget? Did you encode them into your objective function?
Yes. So because, for example, in cloud computing, we can actually really measure how much it costs, and then we can also build a cost function that is money over all these parameters or cloud instance. So it just becomes yet another cost function. And then cost, latency, and throughput will be put in this multi-objective optimization procedure. And you can give us constraint, because constraint optimization is just a special case of multi-objective optimization. So we'll find a solution that fits under your constraint. And within that, we're going to explore trade-offs.
Okay, thanks.
Thank you, Professor, for the really impressive presentation. So just have a very quick question, because we are coming from e-commerce companies as well. So for analytical purpose, sometimes, for example, if the marketing is doing certain campaigns, they want to have a conversion rate. It's actually combining a lot of transactional data and behavior data all together to come up with a certain kind of metric, which is super important. But still, the data flow can be very comprehensive. But what's your suggestion regarding to allocate a resource or prioritize such kind of like metric calculation?
So the question is, do you believe you have this target metric, right? Do you think by choosing cloud instance, by choosing different parameters of this job, it would affect your metric? If it will affect your metric, then we can learn the dependency as a function. So that means at runtime, we observe your target metric, we will observe the current configuration and the entire environment, and we use deep learning to build a function. And that function will be used in this optimization procedure to choose the configuration that suits your need the best. Okay? So if you have a real use case, I'll be very happy to talk afterwards, because after all, EO invested a lot on this project. We would like to see some, successful use cases at the end of the project.
Cool. One more question.
How difficult is it to get the autoencoder trained in the first place?
Okay. So I skipped some details. It turns out for the autoencoder approach, we don't even have to do online training when a new job comes. We only do periodic training, like every night. We do the training, and when a new job comes, we simply run through the autoencoder to get its workload encoding, and we put that into the predictive model. We can do everything in online fashion. There's not even incremental training. But then it has to go through optimization to really make sure we don't lose accuracy. So there's quite a bit of optimization there. So overall, you have to hope that, you have to kind of live in this belief. The optimizer gets to see all workloads, for example, that have been running under Spark in this cloud setting. Across this wide spectrum of workloads, there is similarity. There's something we can leverage from the past observations. It's different from the previous talk where they're trying to tune one program at a time. But here, the optimizer gets to observe a wide spectrum of workloads, and something can be learned together. So for a new job comes, we can map it to the closest workload to leverage knowledge. We don't have to retrain.
Cool. Okay. Please join me in thanking Professor Diao one last time. Thanks.
You're welcome.